So we're going to start this next section with some data collection, and I'm going to send around a piece of paper, and I would just like you to write your height and your, it's not a deep study, just your height and the institute you come from. Okay. So that this afternoon's exercise is you're going to make your own data frame and your own visualizations of the heights of different institutes. You're writing the agenda as well? I'm trying not to. I'm trying not to be heteronormative. So,
I have 7
sorry?
7 different things.
Do we need to write our names?
So, no, it's anonymous. We don't have GDPR approval. So there's no personal data here. It's just a row is an institute and a height. This is probably the least controversial thing I think we can do in data collection. Let's see. So, and it's not deep data, but it's data, and it's something that we can type into and make a data frame out of and play with a little bit. Okay, so moving back, where were we? Well, we're making plots, and we're going to avoid using the data frame directly at the moment, because the easiest thing to do is just to go plot. Oh, did you start your film again, Mass?
Yes.
Okay. The easiest thing to do is just to go plot, and it gives you the box plot for free, but we're sort of building up that concept. So we've got plotting with this tilde, and the tilde just means equals, like it does back in high school algebra, and we'll come back to that. We'll come back to that on Wednesday when we start doing linear modelling. It's useful because it can be used to deal with different data in different ways. So let's go back to making a box plot, and let's keep using this tilde syntax, and let's plot our deers again. So what do we want to do here? Well, we're interested in plotting our deers. We're interested in producing that box plot that we had before. So what should I be having as my y variable here? What's the first variable I should put if I want to plot weight by species? If I want to make this box plot of the different species and how much they weigh, and I want to use this tilde notation, I want to use this equal sign notation, what should I put here? Can someone tell me what I need to put in the box plot function? How should it look? Yeah.
Name of the data frame.
No, we're not going to do that. Let's just use these. Let's just keep the arrays. We're still using the arrays.
Okay.
So we'll use species and weight as separate arrays, just to keep it super simple. So something as a function of something, or
so weight is a function of species.
Weight is a function of species. Yeah, basically that's what we want. So we want weight as a function of species, and that'll give us our box plot. And there it is. So this is just sort of exploring this different tilde notation in different sorts of contexts. We can also do what you were saying and use the data frame. So that's sort of the next step. And there's 2 ways we can do that. One is what you were sort of starting to say, I think, maybe, which was say box plot, and then if we wanted to pick out the different things, we could say, right, deer studies, and then use this $ thing, right, I guess. Remember we had that before? So now we're picking out the weight array, and picking out the species array. And that'll give us the same box plot. So if you try that, that should give you the same box plot. There's another way to do the same thing, and this is one of those syntactic things, and this syntax is going to become useful when we're doing linear modeling again, and when we're doing aggregating and things like that. Is there anybody blinded by the sun that wants the things down again?
Maybe a little bit.
Yeah, now we're getting reflection. Sorry?
I don't get why it's not the opposite around so it's study. I would say it was study species and then study.
No, because we've got the y as a function of the x. So the outcome as a function of the input. Like back in the algebra stuff.
Use the comma, perhaps.
Sorry? Oh, sorry. Thank you. I should have got it. That should be the tilde. Sorry, that's what you're asking about. Sorry. This is supposed to be a tilde one. Sorry. So there we go. Same box plot if you use the tilde. I wrote the comma as a mistake. Oh, sorry. I thought I got you. Is it this one? I think I tried every one but that one. There we go. Yeah. Okay, so now we've got this tilde notation that we're using, something as a function of something else, and we're using the data frame. There's a sort of more, yeah?
I need hands-on help. I've lost all my windows.
Oh, that happens too.
Yeah, okay. Yeah.
Okay. So now we're plotting the weight as a function of the species, and we're using the deer studies data, and we're using the deer studies data. So what I'm going to teach you now is a syntactic trick that becomes useful when we start using other functions in the R sense of there's a function that takes an input and gives you an output that also use this tilde notation. And that's more efficient. And that is that we can save writing the data twice. So let's go weight as a function of species, and we'll tell R which data frame we're interested in. And that'll give us the same box plot. So now we're saying here, we've got a function, right? And this function is the box plot function. It could be the plot function. On tomorrow, I think, you'll see something called the aggregate function. On Wednesday, you'll see something called the linear modeling function. And all of these functions take the same arguments, the same kinds of arguments. That is the data, which is a data frame. And so your Excel spreadsheet, which we've called deer study. So that's our Excel spreadsheet. That's one of the inputs. And the other input is the formula that relates these variables that we're interested in to one another. So they're the two inputs into this function. This function outputs a plot. Other functions might output a table or a statistical test or a model fit or other things. But this is very general, and we'll come back to this over and over again. So basically we're telling R, I'm interested in this data, and I'm interested in relating this data in these ways. Now give me a box plot. So when we send that down to the console, that's the information that we're giving it. Okay? Okay, so this is the plot we've got, and it's not attractive. So let's now. This is sort of an advanced topic. This is to show you what you can do with plots. So you can give it more than just this information. You can give it more than just information about which data frame you're interested in and which variables you're wishing to relate to one another. There's other things about plots that you can change. You can change the color of a plot. You can change the label of a plot. You can change the labels you have on the X and Y axis, and they're all inputs to your function. You just have to tell R that that's what you're interested in. So let's make a pretty plot, basically. Let's make a more attractive plot. Using this basic syntax. This is the basic syntax. We're going to elaborate on that by telling it to pick out specific colors to represent stuff and putting labels on stuff. That's all we're going to do. So I'm just going to copy this one. And then I'm going to add some inputs. And if you're asking me how I remember the syntax to this, I don't. I cut and paste it from an old exercise, or I look it up online and I forget everything. Thank you very much. So we want to give a color to our variables. So what we'll do is we'll say variable color is equal to, and as you notice, I'm looking intensely at my notes because I don't remember any of this, and that's entirely acceptable. We're concatenating the colour gold, because I'm Australian, and the colour green. And so that's the colour. Then we're putting a comma to give it another input. And we're putting main in. What's the main? Main's the label that we're going to put at the top. So that's just the title. Dear weight. The X lab, which is the species. That's the label of the X-axis, and you'll notice that I'm putting these in quotation marks. And the reason that I'm putting these in quotation marks is because I want R to interpret them as items of text. I want R to say, here's a chunk of text, please write that out explicitly as this chunk of text. And if I don't do that, what R will do is it'll look for my species variable. And then, instead of putting on the X-axis the word species, it'll put my list of 60 species names. Because that's what R thinks species means. And that's not what I want. So when you put things in quotes, what the quotes do is say, please evaluate this as a chunk of text. And then ylab, which is the label for the y-axis, we'll just do the same. Weight in kilograms. Put our units on because we're good scientists. And there we are. So that should give us a good looking box plot.
Just one question.
Yeah.
About the labels.
About the what?
About the labels, the X and Y labels.
Yeah.
Isn't there any smart way to get those from the headers of the
otherwise there's only.
I mean, I always wondered why I do have to type in all these.
If you do plot data frame, it'll spit everything out automatically.
Okay.
But I'm trying to walk people through the difficult way so they know what's going on. Yeah. Then I think you could just do color. So plot, color, plot, data frame, color will give you the same thing.
Okay.
So there's an error somewhere. I've got too many brackets.
Maybe it's outside this.
I fixed it. I fixed it now. I had an extra bracket down here. So fingers crossed. What happens when I run this? We get this very Australian looking figure. So plotting functions can be really, really complicated and have lots and lots of variables and lots of information.
It's because you
But what matters most is the fact that you input a formula that specifies the relationship between the stuff that you're interested in,
yeah.
and you tell it which data.
So anything with the graph.
Why do we have to put parentheses around the concatenate function?
You actually don't think you have to. I think that's just me being paranoid. I tend to over-parenthesize everything. Let's see. Yeah, that's just my bad habits. Sorry. So that'll work without the parentheses around that. I sort of have a basic philosophy of better too many parentheses when you're running complex simulations and stuff. So did everybody get the Australian looking graph?
No, I'm a little bit behind.
Okay.
Yeah, great.
Sorry? Oh yeah, of course, sorry. There we go. Yeah?
Why does my plot not have the dots
Because you don't have outliers, we randomly generated the data, so we're all going to have different data. So you don't have any outliers in your data from what you generated. Yeah? Yeah?
What if we wanted to have the weight start at 0? Or something?
Yes? No? Because you want to be a good scientist and show your scale properly. That's a good thing to do. So that's one of the variables, or that's one of the arguments in this function. I'll try to be precise. Then you would say what you want your y-axis limit to be, right? So your y-axis limit is y-lim, and then you want an array, and that array should be 0 to, say, 150. And you use the concatenate function to make your array, and your array here is 0 and 50. So your argument there for your function is 0 and 50 are my y limits, and that gives you a more honest plot. 0 and 150. So you can, there's lots and lots of different arguments that you can put into a plot, and this is one of those things that is a good thing for self-study and to mess around with when you're making your own plots, and to mess around with when you start playing with ggplot if you get that far. And the first source of information for what sort of arguments can go into a plotting function is the help file for plot, which is here. That'll tell you what arguments it takes, what values those arguments should be. You can change different dots, different colours, all sorts of things. And you can also do the same for box plot if you want to know about the box plot. Yeah?
You could put the max value to the y-axis as the maximum value of the weight.
Yeah, that'd be a reasonable one for this particular case, yeah. And that works in this case like that. Shrinks it a bit. Yeah. Okay, so that's plots. Any questions about that before we move on?
What did you just do?
Oh, don't worry about that. That's a bit. That's too. I put a function inside of a function, used as an argument, so don't worry about it. How are you going up the back? Do you have anything that you need covered? Any questions that we can take? something broken up here?
Yeah, I don't know. I think it's because there's one.
Take out the extra percent, take my Okay, so that's the basics of plotting. We'll have a little bit more as we go along. And there's lots and lots and lots and lots you can do with this. I'm not going to go into great deal on visualization. This is just to get you started and to start looking for your own resources. So that's plotting. So let's move on. Any questions, any general questions about plotting? Conceptually, syntactics, or anything like that? No? Okay, so the next thing we want to look at, the last thing we want to look at before we come back tomorrow and start talking about statistics, is statistical functions. Some basic statistical functions and what they look like. And so I'll cover some of the concepts for this sort of stuff tomorrow, but just sort of to get you started on calculating things that you might calculate using a statistical function. And sort of the most simple model, the most simple statistical function in R, probably the most basic, most intuitive one, is the mean. What's a mean? A mean is just the average. A mean is just adding up all of the numbers in an array and dividing them by the numbers of values. So here you've got your data, there's an average height in this class, and that average height is calculated by adding up all of these numbers and then dividing them by the 35 people that are here. And we can do that explicitly, or we can do that using a built-in statistical function in R called mean. So let's look at the mean, say, of the weight of all of the animals we've collected. What's the mean weight of all of the animals? My mean weight is 71.79641 kilograms. Your mean is going to be slightly different because we use different random number generators to generate the data. But sometimes we're interested in specific means. So we might be interested not in the mean of, say, all of our animals, but we might be interested in, say, looking at the difference between the weights of deer and reindeer. So how do we extract that information out of our data frame so that we can do operations on it? Because basically what we want to do is we want to make sure we've got flexibility in the kind of inputs that we put into a function so that we can get that information out of that function that we want. And here we're getting a mean, but we're not getting a mean of the relevant information. So how could we do that using our data frames, or using some of the other information that we've got encoded in the other arrays? How can we extract information? So what we're going to talk about here is another programming concept that you're going to need. And I know that sort of concepts are starting to pile on top of one another, but we'll come back to these concepts. And this concept is called indexing. So what indexing is kind of what the word suggests. It's, if something's indexical, it just means to point, to indicate. So what you're doing is pointing. So you're pointing at specific numbers in your array. So we can do that, say, for the weight array, and say, well, I want to know what the fifth, I'll do this down at the command line because I don't need to save it because I'm just doing a demonstration. For this part, I want to know what the fifth value of the fifth variable is. So the value of the fifth number of my weight array is. So I'll take my weight array and then I'll use square brackets. So whenever you see square brackets, it means indexing. It means pointing. And I will point at the fifth array. Sorry, the fifth value in that array. So picture in your mind your Excel sheet, your list of numbers, this list here, and I'm pointing to number 5. So the 5th deer that we measured is 62 kilograms. Is that okay? So that's not so useful for what we want to do though, because we want to point at all of the deers.
Where are the square brackets? Sorry.
Sorry, oh, the square brackets?
Yeah.
Do you have a Mac or a PC?
Oh, here they are.
Yeah. It's the Alt-GR button again.
Yeah, 8.
Danish keyboards are not made for programming. So we don't want the 5th number, we want all of the deers, for instance, and we want all of the reindeers. So how do we do that? We still want to index, we want to point. We want to point simultaneously to everything that's also a deer. So we want our weights again, and we want to point. And we want to point to those things where species is equal to deer. But we're going to do something weird. We're going to do a double equal sign. And I'll go over why you do a double equal sign in a second. And remember, deer here is a text object. It's a text item. We don't want the whole array called deer. We don't want an object in R called deer. We want a value. And if we're talking about values, when we've got sort of text, it needs to be in quotes. So we want to point to those values in the weight array where those in the corresponding species array, the value is deer. So we want to use one array to point to another array. So you can imagine, it's best to draw this. If you've got your deer, 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 reindeer, reindeer, and you've got some number here. What we're going to do is, we're going to single out these ones first, and then use that to point over to this array to get those. And that's what that little piece of syntax does.
It's just a question, so it's sort of assumed in that you're referring to the data frame and not...
Yeah, but you remember we made weight as well as
Yeah.
an array before we put the data frame together.
Yeah.
So that's what this is using now. It's not
Yeah.
using the data frame.
Okay.
Yeah. So if the data frame wasn't there, this would still work. This is that species array that we used before,
Yeah.
and the weight array that we used before. So we're not actually in the data frame at the moment. And I know that's a little bit confusing, but I thought it was useful to not have to go deer study colour sign.
Yeah.
Yep. And we use this double equal sign because equals can mean two things. Like, think about the concept of equals. Equals can mean two things. Equals can mean that we're determining something's equal to something. So we're taking this A that could be anything and pinning it down to 30, or it can sort of represent a tautology, where it can mean is, where say 30 is 30, or 50 is 50. Or in this case, places where species is deer. And when we want to say is, then we use the double equal sign. And that's just a programming convention that's the same in all languages.
Repeat that.
So equals can mean two things. Equals can mean that we've got a variable that could in principle mean anything, and we're going to pin it down to a value. So A equals 30. Whereas when it's a double equals, there's already an existing relationship that we're interested in. And that's this is. Ontological is.
But that only works because we created the data frame.
Yeah, well, if there was something called weight, so if I put beer instead of deer, there's nothing in the species array called beer, so it'll look for it and won't find it, and it won't give us anything out. So it's only because we've said there's things in that data frame that are called deer. So it says anywhere where this occurs in this array, then basically this is the species array, and it's saying where in the species array is there a deer. And that's why it's a double equal sign. So it's sort of a pre-existing thing. Is that okay? Very philosophical description of the distinction between those two. So that'll pick out only the weights of the deers and not the reindeers. So we can do the same thing just for the reindeers. And that'll give us the weights of the reindeers. So this is starting to be useful because we've picked out the weights of the reindeers and the weights of the deers. So now we can ask, what's the average weight of reindeers and what's the average weight of deers? We can do that by going another step with this syntax. So basically we're saying we're interested in the mean, and the input we want is the outcome of this indexing. So the outcome of this pointing. So we want to first point to, so you read this sort of, you read these more complicated bits of code out from the inside out. So you say, I want only things that are deers, species equal deer, and I want the weight, and I want the average of that. So let's do that. So I want species equal to deer, and I want to index that, so I want to point to those things in the weight array, and I want to look at the average of all of that. So that'll give me the average of my deers. Spelling error. So that'll give me the average of the reindeers. And that's hopefully close to 60 and 80 because that's what we told the random number generator to generate for us. Okay? So this is how, so this is not the way that you'd necessarily do this, but this is giving you a feeling for indexing and a feeling for doing stuff with indexed code. And I think this is important to do because if everything's sort of locked away in a data frame and all of your operations are always on data frames, you don't necessarily get a sense of the more data processing, data munging that you can do with R that you sometimes need to do if everything's already pre-cleaned. So this is to deal with a little bit of mess. This is to create a little bit of mess in our lives. There's a more efficient way to do this, and this is the way that allows you to do something where you've got more categories. So imagine if you've got some of this horrible data where there's 9 million lines of code, and you've got 100 different categories, and you want the average of every single category, so you have to do this 100 times. That would be very inefficient, that would be very nasty. So what you might want to do is to make a table. And a table of the means, or the averages, of all the categories that you're working with. And there's a special function for that. And it's called aggregate. And aggregate's good because it uses the same syntax that we were using before for plotting. There's something as a function of something. So how does this look? Let's make a new object. So we're going to make a new object called a mean table. So this is our table of means from our deer study. But imagine this could have 100 different means. In our deer study, we've only got 2 categories. Our mean table is the output of a function, and the function that we want to use is this one called aggregate. Now aggregate's a function, it takes inputs, it spits out an output. It's like the plotting function. The output it spits out is not a plot though, it is a table of statistics that you're using to aggregate your data. And the inputs are the same though. So the inputs are a formula for relating the different the different variables that you've got in your data frame, and the data frame that you want to use, and an extra thing, which is the statistic that you want. So you could be interested in the mean, you could be interested in the median, you could be interested in some measure of the variance, you might want to look at the median for the deers, you might want to look at the mean for the deers, you might want to look at how fat the distribution is for the deers, and you can do all of those things, and you have to tell this function which one you're interested in, otherwise it won't work. So let's do that. So we put our formula in first, and that's just weight as a function of species. And our data is just our data frame from our deer study. And the function that we want to use is the average. We want to get the average. And if we send that to the console, we'll get a new object. And that object is a piece of data called mean table. What does it look like? It looks like that. So that aggregates the data and calculates the mean using the formula that we gave it. So it says, treat weight as a function of species and give me the average for the 2 species separately. And you can imagine if you had 100 variables, that'd be really nice, because then you get this list of averages for your 100 different categories that you've assigned your data to. And this is why I introduced that tilde notation, because it keeps popping up in different contexts. And the mean table, that's just something we called it because it makes sense to us. We could have a median table. And that would be the same. That would be weight distributed as species. And the data is the same, it's the deer study, but now we're interested in the median.
Was there a function you could repeat the previous line so you just delete it?
Oh, that's just cutting and pasting.
Cutting and paste?
Yeah. But you can also do it at the command line by pushing up. Yeah. But then you don't have a record of it if you haven't written it down. No, I'm just control-C'ing when I do that. So let's have a look at median table. Hopefully the values are roughly the same. They are. Median's a bit different, so that means that the middle number for weight is slightly different to the mean. Sorry? Yes. Oh, you have you've got you've put the capital up here, and then you've tried to see it, and you've used a little, so you just, that's all it is. That's it. That's it.
Mine doesn't spit out the, you've got your species and weight.
It doesn't give you the labels?
I get the table up in the thing, and I can see the table, but it doesn't come.
Yeah, it comes up there.
Oh yeah, then you have to type it separately. Remember, if you assign something to a, if you have like A equals something, it suppresses the output. You only get the output if you then type it in. Remember we did that at the start? So type mean table down in the command line. So basically, what happens when you use that? Have you called it? You might have called it. And then try writing. Source runs the entire script. Yeah, the source will run the entire script for you, and run will just run that one.
Is it good practice to do that, or does it matter?
And just to practice again, we can do the same thing for standard deviation. I'm just cutting and pasting, changing the name. Standard deviation table. And SD means standard deviation for R. So someone programmed that, someone called it that. They could have called it something else, but that's what they called it. So that's what R interprets. That's what that function's written to accept. It can only accept certain things in that argument, in that function argument. It'll accept SD or mean or median. It won't accept anything random. So that gives us this SD table. And remember, when you're assigning something, when you're assigning a value to something arbitrary, so like A equals 2, and you run that from this script line, it doesn't immediately print it out. All you're doing there is you're telling R, I want you to remember that A is 2. Don't necessarily tell me about it, but remember that A is 2. And then if you want to hear about it, you have to ask R. So you go down to the console and say, can you tell me about A now? Or can you tell me about standard deviation table? And that'll give me the standard deviations for the two arrays. And we'll talk about what that means tomorrow.
Is there a shortcut for changing between the windows so you don't have to click with the mouse every
Oh, they're
time?
probably
Control 1 and Control 2.
Control 1 and 2.
Windows.
Okay, good, thank you.
Control 1, Control 2 should do it on Windows.
That's
For
where,
Mac users, I'm sorry.
that's where software carpentry comes in handy.
Yeah, shortcut.
Ja.
Somebody on Mac may know how to do
Ja, det er mega irriterende, man kan vinde musen, når det er.
it. Yeah, I'll write it up.
I have lots of bad habits. So. Okay, so that's the aggregate function. And that's useful for getting statistics out. So we're starting to sort of do statistical things. So we're actually, well, what you can see is that these values are the same as what we put in. So if we have a sort of a bit of reflection, you see that these numbers here, 60 and 80 and 10 and 10, they shouldn't be massive surprises. Because remember when we generated our data, we said we wanted the variability to be 10 for both, and we wanted the average of the weight 1, which was the deers, to be 60, and the average of weight 2 to be 80. So we've recovered that. So we've done something here. We've done something called parameter recovery. This can actually be a really important thing to do if you're working with complex models. Is you generate some data based on the parameters that you think on the setup of the model that you've got. Here the model's very simple, it's just averages. But models can be more complex from that. You can have linear models, can have models of specific relationships between variables. And it's always a good sanity check to do this sort of thing, to put some numbers in, randomly generate some data, and see if you can extract those same numbers back out. Then you know your model's sensible and makes sense. So that's an advanced topic. But we should be happy that we got the mean out that we put in. So we're right at the point where we're just about ready to do some statistics. So rather than finishing at the point where we're ready to do some statistics, let's do some. So this is the concept that we're going to cover tomorrow. We're going to do a t-test. We're going to talk about t-tests all day tomorrow. So let's do a t-test. What's a t-test? A t-test in the context of R is a function. You'll learn about this function tomorrow in detail. Function takes an input and spits out an output. And what we're going to see now is something that takes a relatively simple output and spits out a relatively complex output. And that output is going to be all of the statistics that you need to get out of your statistical test in order to evaluate whether or not there's a difference between reindeers and deers. So let's do that. The way that we do that is to write t-test, which is the function for running a t-test. I don't think t-test takes it's going to be slightly annoying. I don't think t-test actually takes the tilde syntax. I don't think it does. Let's try it. LM does, but this doesn't. I'm pretty sure this is not going to work. But we'd want this to work, right? Because everything else works with tildes. Ah, it works. I'm happy. Okay. So, what have we done here? We've got a function, and the function's going to do stuff to some objects. And here, the stuff that we're interested in is a formula. Weight as a function of species. That's what we want to know about. That's exactly the same as for our plot. And that's exactly the same as for our aggregate function. And what data are we interested in? Well, we're interested in our deer study data frame. So here we're telling the t-test function what data are we looking for? The deer study. What relationship do we want to see? Weight as a function of species. And then it's going to spit out all of the statistics that we need in order to test the hypothesis of whether reindeers are heavier than deers. And that's what we'll do tomorrow. We'll talk about what that means. Here you get all of these different things that you need. The mean of the two groups. The 95% confidence intervals, which I'm not going to cover because I don't really like confidence intervals. I think they can be very misleading. So we're leaving that out. You get your p-value, which you can see here is very low. You get your degrees of freedom, and you get your t-statistic. And we'll talk about all that tomorrow. Yeah?
I always have a hard time finding out if a standard deviation score is high or low. Does it mean, if I get a score on 57, does it mean that it's high?
But that's your degrees of freedom, that one there. Not your standard deviation. But your standard deviation is going to be on the scale of the variable that you're measuring. We'll talk about that tomorrow as well.
Yeah.
So if you're measuring on a scale that goes up to 1,000,
Yeah.
then a standard deviation of 10 is really low. But if you're measuring on a scale that goes up to 50, then a standard deviation of 10 is a lot of variability.
So my standard deviation is on here 7. Is that high or low?
Standard deviation should be the one that you... Where are you getting that? Are you getting that out of
I'm
the...
just running SD table.
Oh, yes. 7's low compared to what you put in. But so basically what you should get out for SD table is what you put in. When we sampled the deer study, when we made our data for the deer study, we said let's randomly draw from a normal distribution where the standard deviation is 10. And you should get 10 back out again. But you won't always get 10 back out again. Sometimes you'll get 7, and that's fine. That just means that you've got the sampler that the seed in the random number generator has given you a value of 7, which is not impossible. So that's fine. And we'll talk about what standard deviation means tomorrow. We'll talk about what mean means tomorrow. We'll talk about how to use them to do a t-test. We'll talk about what degrees of freedom mean a little bit. I always sort of mess that one up. I strongly suggest people to read the book because he's got a fantastic explanation of degrees of freedom that I can never get right. I'll flag that as one of my major teaching weaknesses. We'll talk about what a p-value is and how to interpret it. And we'll talk about how to interpret this table and use this table, which is what you really want to do. So that's the goal for tomorrow, is to get through t-tests and different kinds of t-tests and see all the formulas that are relevant. So what you've done today is quite a lot. You've learned about how to do indexing in arrays in R. You've learned about some basic statistical functions. You've learned about how to generate summary tables. You've run your first statistical simulation and a hypothesis test of that simulation. You've run your first parameter recovery study. And you've seen a little bit in action how some of the concepts and assumptions that you have to make can be transformed into a numerical context. And we'll take all of that forward tomorrow. We'll start talking about looking at some real data to look at in the context of hypothesis testing. So we're not modelling yet. We're just doing hypothesis testing. And then on Wednesday, we'll do modelling. So as a consolidation exercise, what I want you to do is we'll have a break, and I'll make photocopies of this, and distribute the photocopies, and you have to make data frame in a relatively efficient way and construct the relevant plot to say something about the data and construct tables, summary tables like we did using these aggregate functions, and to run a t-test to tell me if there's a significant difference between the heights of people in IKS and IKK. We'll leave out the 2 DPU people. I'm sorry. we have, and we'll put in our limitation section that we sampled insufficient number of DPU people for this particular study. So after the break, that's the exercise until 4 o'clock. Self-paced, and I'll go and get some photocopies.